Welcome back to Munro Live. So, of course, this is not an actual vehicle that we are reviewing today. We're actually looking at a material and a process from WEAV3D. We do have Lewis and Christopher here to help talk me through these parts. And I will give you a little bit of warning. This is pretty much going to be a nerd session for us. In my past, my thesis was actually an injection moldable carbon fiber. There are current ways that we use carbon fiber lots of times in epoxies and thermosets. We're taking sheets of carbon fiber, laying them up. Well, those processes are very expensive and there's an awful lot of scrap. And having that type of scrap and those types of processes with a very expensive material, it just puts it out of reach of a lot of manufacturing. For me, I wanted to basically throw pearls before swine. I wanted to take that carbon fiber and I wanted to directly use it within injection molding, which is like the lowest of the low cost, and wanted to see what would happen. Now, you have taken that type of material and other materials, and you're working through lightweighting and these processes. So could you kind of explain what we're looking at here? Or explain more about your company?
Sure. So my name is Chris Obersty. I'm the President and Chief Engineer at WEAV3D.
I'm Lewis Motion, CEO of WEAV3D.
So WEAV3D is basically a material manufacturing company that's focused on high rate production of composite lattice structures. So we make something like this. So this is basically a mixture of tapes, glass and natural fiber in this case. But these are thermoplastic tapes. So they actually have a polymer in them already. And this allows us to integrate these materials into other plastic forming processes like injection molding or thermoplastic compression molding. So the samples that you see on the table here, these are all thermoplastic compression molded parts, varying types of substrates and materials like that. But what we can do with these, traditional forming processes is provide them with a structural skeleton, what we call rebar for plastics, in the form of these lattice tapes. So just to give you an idea here, this is an example of a recycled non-woven material called shoddy. It's oftentimes used for noise and vibration damping. This particular one is a polypropylene PET mix, also has like some cotton fiber in it. But they've compression molded this, so it's very weak, very easy to flex.
So this is the type of stuff that is often used on carpet backing within a vehicle.
Yep.
It's very light, it's a pulp material, it's a recycled material, very, very low cost. Mm-hmm. So you're taking that with a resin, compression molding it, making something a little stiffer,
yep.
But is not stiff enough.
No.
Can I use that yet?
Not yet. So if we then add a very light layer of glass reinforcement to this in the form of a lattice, it gets way stiffer, but it's still not super stiff. So for the super stiff comparison, here's a piece of 20 gauge stainless steel as your reference.
Yeah, I'm not going to bend that.
You're not going to bend that. Try doing this with carbon fiber on top of that shoddy.
On top of just this?
That is carbon fiber and shoddy. That is equivalent stiffness to 20 gauge stainless steel.
So I'm taking that.
You're taking that sheet,
which as a core is almost the full thickness of the material.
Exactly.
So
you're only adding a really thin amount of tape to get the performance that we're getting here. So this is all about kind of how do we use a cheap material to make up the majority of the volume of the part while still providing the performance that you want for a structural or semi-structural application.
So this goes back to, as I said, throwing pearls before swine. Wait a minute, the carbon fiber, that's what I'm using on my $300,000 supercar. That's gonna be the whole hood. That hood is huge. I want that light weighting. It's gonna be in a vacuum bag. It's gonna go in an autoclave. It's gonna have all those layers built up. Why? I can take that same type of material and I can use it somewhere cheap. Mm-hmm. And I don't really like saying cheap, low cost, high volume. I'll use it in a different way. So let's say I was taking the carbon fiber, the glass fiber, I'm using it in a part like this. Mm-hmm. This is a very, very lightweight NFPP type material.
Yes, and this is an IP topper. So this would normally go on the dash of the car. Today, you can make this with NFPP, but you generally have to back inject it. So you're going to be using a fairly high weight NFPP, 1700, 2000 GSM, and you're going to be injecting ribs all over the back of this part. So if you look at the close up on the part, you can see this tool actually has ribs in it, but we covered those for this trial.
So let me grab another part for comparison. Yeah. So as you said, this is an IP topper. Mm-hmm. This is also an IP topper. This is an NFPP material, and here are all those back injection ribs. Now, the only good thing about this is, yes, that's giving me my rib structure for my stiffness. I'm also getting some attachment points within this, but I am compression molding this part, then I am injection molding this part. It is the exact same size. So I need two large tools of the exact same size. I'm not saving money by making this just out of injection molding. I have to do both. Other than my attachment features here, I can get roughly the same stiffness provided just within that compression mold and those layerings.
Exactly.
Okay.
So the goal with this is we're basically taking that tape material, replacing all the rigidity that you're getting from the ribs in the injection molding, and in some cases even allowing you to use a thinner NFPP to start with. So one of the key things with this design that you see here is what we call homogeneous design. So the spacing is even everywhere in the part. I can give you an example over here of a non-homogeneous design. So this is not NFPP, it's actually a cellulose non-woven material that was developed by Volkswagen. But you can see there's a lattice in this part, and that lattice has an uneven distribution within the structure. So in this particular case, we're both reinforcing this material so it's easier to form, but we're also providing an additional stiffness in this part by tailoring it where it needs to go in the part for performance purposes. So that means I can use less of the continuous material and still get the performance that we're aiming for in the finished component.
When I am injection molding, you have ingates within an injection mold. So however many points that I have to actually injection mold the fiber. I'm injection molding a short glass fiber. It is coming into the tool and then it has to move and it has to spread out. Those fibers all get an orientation based off of the gating and the sequencing of the gate, which means that I actually do have different properties across this part depending on where I'm at. I'm gonna have a knit line where those two pieces of molten material are coming together. That knit line I have to really, really manage because that's my weak part. That's where I'm gonna break. When I was trying to injection mold carbon fiber, that was one of the challenges that I had. Part design and tool design really mattered because any of my knit lines, you could literally see all the fibers angling and pointing towards these knit lines, these weak points. All right, so taking my idea, what I worked on, but you're completely choosing what orientation you want
Exactly.
in the compression mold.
Yeah, so this is actually good for a couple of reasons. One, for those knit lines, if you have a continuous fiber, so unlike in an injection molded part where the fibers themselves are short, we're talking a couple millimeters, maybe less than a millimeter depending on what your distribution is. Or if you're using like a long fiber product, maybe you're like 10 millimeters or so.
I was dealing with a glass fiber. Input into the injection molding machine was 5 millimeter glass fiber. Then we burnt all the resin off to try and find out as it's going through the screw coming out, what are we left with? 0.2
It's
was
so
my
short.
average.
There's so much attrition. Yeah. So this is a problem though, because the shorter the fiber, the less load transfer you have from fiber to fiber. So if you've got two fibers that are really short, that there's a gap between them, then the load has to go through the polymer to get to the next fiber, and you're losing performance because you're not cohesively transferring load.
So a little bit more on the nerd moment. I will go back to polypropylene just because I know polypropylene. We have the polypropylene resin. Now, going all the way back to chemistry, and you're looking at all the little polymer chains, we have, basically it's also a carbon type material. We have all these polymers that have bonds that are trying to reach out and grab something. Then we have our fiber that we're putting into that polymer chain. The fiber acts as scaffolding or a lattice work. So those polymers that might be flexible and might be weak on their own, they now get to reach out and they get to grab onto that lattice work. If I am doing that with glass fiber, 2.7 grams per cubic centimeter, I'm looking at how many fibers am I going to have across an area or a volume. And that's what does this now have to grab and bond onto. Now I'm throwing in carbon fiber. Carbon fiber, basically 0.8 to 0.9, which means in the same volume of material, I have a lot more fibers. So I don't have to reach out as far to grab onto something to give me that strength. Carbon fiber and glass fiber can actually be the same diameter. I'm normally working at 0.8 microns type thing. So I can actually have more things to grab when I'm using that type of carbon fiber if I'm the polypropylene in the matrix than if I'm using the glass fiber. Now we do have both, and there is a place for both, but that's really what we're talking about, trying to give whatever resin is in here, these long chain polymers, something that I can reach out and grab onto that's going to give me extra strength. And the amount of things that I can reach out and grab onto within that area is where I'm going to get an increase in that type of strength. So, sorry.
Going back to that rebar for plastics concept I mentioned at the beginning, what these tapes are doing, to your point, is they're giving you a continuous fiber that runs the entire length of the part so that you always have something to grab onto, basically.
And it's transferring that load.
Transferring it all the way through. Yeah. So you're not relying on the polymer to connect the fibers anymore that are in the mix. You're using the tape to carry the most of the load. And what this does is it actually concentrates stress away from the molded plastic. So what we've found in our experiments and some of the applications that we've tested is you can actually control whether the fiber breaks first or whether the polymer starts to break first, depending on the relative ratios and the relative stiffnesses of the two materials. So that kind of brings me into this part. So this part is actually an automotive door structure. So this was designed by Clemson University in partnership with Honda as a way to replace a steel door assembly. They went to a carbon fiber nylon organo sheet, and then we were asked to come in and redesign the organo sheet into polypropylene. So the way that we came up with this design is it's actually a sandwich structure. So you have this lattice on the top and bottom sides of this part, and inside the middle of the part you have this polypropylene sheet. This is an unreinforced polypropylene. And what we see when this part actually gets loaded for like a side pole crash type test is the part flexes and we crack on the fibers on the backside, but then the part continues flexing because the polypropylene is still fine. So then when you take the load off, this actually rebounds back to its original shape as if there was no damage to the part at all, except for the small amount of surface cracking you see in the fibers.
So one important thing to make mention of there is when we go into a crash test, I'll give an example from an instrument panel. If I have the mannequin sitting in the seat, the airbag is blowing, I have to blow through that instrument panel. We actually have basically nets and screens that will catch any little bits of material that are now flying out of there. We can't have that. We can't have some piece of shrapnel now flying at you as you're an occupant. So if I can tune that to say, yes, I may crack, but I now have 2 layers of reinforcement. I would only crack on that outer layer. Yep. That goes back into now that engineering thing. When you're in your solids class, you're looking how things actually break, how stresses, the types of cracks that they cause. That's fun too. I'm really having fun today. So that's important. If I can actually tailor my part for that use case, it provides a benefit to me.
Not only can you tailor the fracture, but you can actually tailor the fracture mode and the duration of the fracture modes. We had a lot of fun with this project. This was we do a lot of simulation-driven design. So we're using some Altair HyperWorks tools to do this. And this lets us basically predict how the part is going to fail, whether it fails in the fiber or the polymer. And then we can even get some predictions of like after that fracture occurs, how much more load can it take? So if you look at a traditional stress strain curve for a composite, it's pretty much a straight line and then it cracks and you're done. If you look at a traditional stress strain curve for injection molded plastic, it's kind of this long curvy bit. If you combine these two, you actually get both. You get like a straight portion and then you get a bunch of cracking and then it drops down to a plateau and then it plateaus for a really long period of time. So what you're effectively getting is high stiffness, high strength, and high toughness all within one package just by tailoring your relative mix of materials. And I didn't point it out earlier, but in this particular part, because this is thermocompression formed, so it starts off as a big rectangular sheet that you heat up and then you stamp and then you trim it off. In this area up here where the window is, you're going to be trimming all that material off, so you don't want to pay for it. So in this particular design, we actually used a much higher density of tape from about here to here in the part, but up in the A and B pillars, where you're going to trim this out anyways in the part, and it's going to get glued onto another structure that actually provides its stiffness in this area. we could go much lower density on the lattice. So this white that you see here, this is actually just the polypropylene showing through. There's no tape in these opening gaps. So you're not paying for this material. And what we found was we were about half the cost of the carbon fiber organosheet, and we had 63% less trim scrap by weight because of the fact that we weren't paying for all this material out here that had to get cut off. It was basically just polypropylene, and polypropylene is cheap.
So I want to get into that a little bit. When I was doing my work with carbon fiber, everyone was asking why. Carbon fiber, it's this really expensive, very technical material. Why am I putting that into something that's so cheap? And when we talk about a filler in injection molding, we normally go by weight percentage. We would say that's a 20% glass-filled product. So 20% of the weight of the part was all the glass fiber that was putting in there. Again, glass fiber at 2.7 grams per cubic centimeter. Whereas my carbon fiber at 0.8, I would talk to the people in purchasing and say, well, per pound, this is so much more. I'm like, don't think about it in per pound. I want per volume. If it is less than half the weight, I can use less than half of that. So I'm like, okay, this is $12 a pound. This is $3 a pound. Yeah, but I only need $6 of that pound to get the same amount of volume. And then, does carbon fiber actually perform better than glass fiber in a one-to-one area? Well, maybe I can pull that back a little more. So if I was doing this in the big sheet of carbon fiber, all of that stuff woven together, I have to throw away all of that. That's scrap. No, it's not worth it. Don't even think about it. You're not doing that. You're only putting it where you need it. So when I'm talking to that person in purchasing who's looking at this in a per meter, per pound type of a cost, I have to explain, don't think about it that way, because that's not the way we're actually using it on the product.
Yep. It's a big challenge for us. Is like everyone wants to know how much is it per pound, because they're used to commodities coming in as a per pound basis, and you have to be like, well, for your particular part, this is 45 cents or something like that. And then that's a completely different conversation, because you're saying, okay, this is how much it costs per part, not how much it costs per pound, because I'm tailoring this to your part. I don't have a generic product that I'm just putting that you have to cut off of a sheet and stack yourself.
One of the things that's really great about our process too is our ability to be able to mix the materials. And so when you talk about using carbon fiber and using that selectively, all the black here is not carbon fiber.
Yes.
This is both glass and carbon fiber. By weight, this is only 7% carbon fiber.
Yeah.
But this entire part is 23% lighter than the all carbon fiber solution with the same performance. And so you can achieve really cool things with minimizing the amount of really expensive material with carbon fiber by only using where you need it.
And this is a glass example, but similar concept of like, if I only need stiffness in one direction on this panel, I can put the glass in that one direction, and then I can put the less stiff other material in the other direction. And that's what gives me a performance outcome at the part that I want, but without paying for that material over the entire surface of the part. So it's really about, can you pick the right combinations of materials in the right place of the part? And what we like to call this is like a hybrid meta material. So the part itself doesn't have one material property over the entire surface. The part itself has meta properties, different stiffnesses in different areas, depending on how much you use in that area, and depending on how dense or open that lattice structure is in that area.
And so instead of trying to layer up different layers of composite to be able to achieve the stiffness or the flex that you might want, you can actually tune that in the lattice design itself. So if you're making something like a helicopter rotor blade, where you want different stiffness and flex throughout, you can do the same thing. Or a shoe sole, where you want some flex and stiffness in different areas to be able to get performance. You can do that and have that tuned performance throughout it. Or you can do something that meets a base level stiffness design, but you want to have higher crash properties in certain areas too. So it's all about the tailoring for that end use to be able to maximize benefits of weight reduction, cost reduction, and maximizing performance, increasing your ability to be sustainable as well, because all the trim scrap you can use on this, you can upcycle it and reuse it in an overmold process as well.
So when I talk to people about some of the interiors of vehicles, of course, they say, it's just plastic, it doesn't matter. Why are we even talking about that? And then I let them know, well, don't you realize that all of these plastics, all of these trims, all of these panels, you know what percentage of the cost of the vehicle this is adding up to be? But yet they minimize that and almost look at those components as being way too elementary for them to care about. This is just the cheap stuff, doesn't matter, anybody can do it. But if I take those types of materials and I use them in a smart way, and I really think about what I'm doing, I can create something that's giving me savings, it's giving me strength, and can actually perform better than what my competitors may be doing. And also, for me, it affects where I'm going to make that part. If I want to know the suppliers that I'm going to be using, how am I going to work with them? Is this just something that I'm going to send out a bill to print to some supplier and I'm never even going to see them, I'm never going to talk to them, they're just going to send me something back? Or is this something that I'm really working on a partnership? And the reason why I really like partnerships is because you can innovate off each other. If you just send this off to some supplier that's going to make a part and send it back to you, all you're going to say is, does it meet the print? Okay, and you're never going to talk to them again. And they're not going to innovate for you because there's no benefit to them. If they make something that is less expensive, if they make something that is more innovative, it's not going to provide anything for them. If I was the engineer at a tier 1 or at the OEM and I designed something that was honestly very, very stupid and expensive to make, the supplier's not going to tell me that because they're going to make more money off that stupid design than off the good design. That's not the type of supplier relationship you really want. You want a supplier and a material supplier that will work with you to tune for your product. In the long run, it will be better, but the guy in purchasing and quality management, they don't want to give up the time and actually show up at the supplier's door. So it's unfortunate.
If you can do that and start looking at things from the system side, like you guys do here, you can start combining things that typically weren't combined and say, okay, well,
we were talking earlier about brackets, right?
Yes.
So one of the areas that we've been kind of pushing on is if you can add structure to these cheap plastic parts that are currently not structural, you can eliminate a lot of brackets and stiffeners that are in the car right now. So if you look at something like the crosscar beam or the IP of the car, a lot of those brackets are holding things up off the beam, and they have to be held up because they're not stiff enough on their own to actually span the width of the vehicle. But if you add extra stiffness to the plastic parts, then the plastic parts can become part of your support structure. So you're kind of expanding what they can do outside of just being plastic surfaces.
You know, and I love that, and I hate a lot of engineers that I work with because of that, because the crosscar beam, just using an example. The OEM has an engineer who designs crosscar beams. That engineer is going to use your fancy tricks and then still put a crosscar beam underneath it. So then management up top is going to say, well, this didn't give us any savings, kill the idea. No, it was a good idea. It's just you had the wrong people working on it. The people that had prejudices in their mind saying, well, I still need this and I still need this. Do you?
Yeah, if you make it strong enough and meet the performance, if the IP carrier can actually outperform the crosscar beam, why do you need the crosscar beam anymore? If you want to take it another level and be like, well, what if we incorporate transmissive material into these lattice structures as well? Now you can eliminate wiring harnesses. That, like seeing at manufacturing facilities, the manually fishing wiring harnesses through vehicle parts to try to get there, if instead the entire panel is your carrier.
All right, so now you're gonna make someone kind of scared about that. Thinking about ribbon wiring that you see in a lot of electronics and stuff like that. So that would be one of these ribbons rather than it being glass fiber, carbon fiber. I now have an electrical conductor that is one of my embedded ribbons. Okay.
We're actually doing some work where we're running those kinds of like aluminum foil ribbons on top of a glass tape. So the glass tape actually also protects the ribbon from fatigue. So you get like a local shielding effect from the stiffness of the glass, and it's also your isolator. So if you needed to, you could even put glass above and below, make a sandwich, and then you just mill a little bit off the surface to make your connection to the aluminum.
Cool. Well, this has actually been fun, and as I said, kind of a nerd moment, kind of a geek out, but I like taking these materials and using them in a different way. This is not one size fits all, and it's not one way of using carbon fiber, not one way of using glass fiber, not one way of using an NFPP compression mold. There are still many things that can be invented, that can be developed within automotive or any product. So thank you very much for joining us today. This has actually been kind of fun. I don't know whether you will like it or not, but this is the type of thing that really interests me. So have a good day.